Hello, my name is Wiagil Widoyoko, student ID 131182004, and today I will be presenting on the creep phenomena for heat-resisting alloys. The content I am covering today will be on the classification of creep phenomena, Larsen-Miller parameter, and the microstructure of heat-resisting alloys. So what is creep phenomena? It can be described as the tendency of a solid material to slowly deform permanently under the constant influence of mechanical stresses. The rate of this deformation is a function of the material properties, exposure time, exposure temperature, and the applied stress. Creep is more severe in materials that are subjected to heat for long periods and nearer to the melting point. For metals, that would be at about 0.4 times the melting temperature. This means that creep always increases with temperature. Depending on the magnitude of the applied stress and its duration, the deformation may become so large that it affects the lifespan of a component and may cause it to no longer perform its function. Information regarding the characteristics of a specimen, as well as the mechanisms of creep phenomena, can be obtained by a typical creep test, which involves applying either a constant load or stress to a specimen at a constant temperature. This graph displays the creep phenomena curve during a creep test where a constant load and temperature is applied. The stages of creep occurring can be termed into 4 points. Once the subject is applied with the load, an instantaneous deformation can be observed as completely elastic. Then, primary creep starts, where the slope of strain versus time is decreasing as time increases, which indicates the subject increasing its resistance towards creep. After that, the subject proceeds to secondary or steady-state creep, where the rate of straining seems to be constant due to a balance in recovery from the strain hardening. The time frame of this stage is of the longest duration, making it the most crucial parameter for long-term applications since most of the component's life is used up in this region. Finally, the subject is exposed to an accelerated rate of creep, leading to its failure or rupture. On the other hand, for short-term applications, the most vital parameter would be time to rupture, indicated by T subscript R, as it can determine how suitable a component is for a certain application. According to the graph, when the stress or temperature applied is increased, the characteristics displayed by the subject includes 1. The instantaneous strain at the time of stress application increases, 2. The steady-state creep rate increases, and 3. The time to rupture decreases. The results of creep rupture tests are most commonly presented as the logarithm of stress versus the logarithm of rupture lifetime as seen on the left. From the graph of stress versus steady-state creep rate, a relationship between the parameters has been evaluated to be the following equation. If temperature is involved, then the equation becomes this one, which happens to be the equation for power law. Creep mechanisms can be classified into 3 types, namely power law, Coble, and Nabarro-Herring. Each classification is associated with either dislocation or non-dislocation-based creep. As seen on the slide, power law is dislocation climb, Coble is grain boundary diffusion, and Nabarro-Herring is lattice or bulk diffusion. Their respective simplified equations are also shown here. Dislocation or power law creep involves dislocations that overcome obstacles such as solute atoms, particles, and dislocation interactions. It normally occurs at 0.6 times the melting temperature at moderate stresses. With that being said, it requires diffusion for dislocation to unlock from solute atoms or climb over particles. Both Coble and Nabarro-Herring are a form of diffusion creep. Coble is a mechanism for deformation of crystalline solids. Coble creep occurs through the diffusion of atoms in a material along the grain boundaries, which produces a net flow of material and a sliding of the grain boundaries. Note that in Coble creep, the strain rate epsilon is proportional to the applied stress sigma. The same relationship is similarly found for Nabarro-Herring creep. Nabarro-Herring occurs solely by diffusional mass transport. important for much higher temperature and lower stresses compared to the case for dislocation creep. It also has the lowest grain size dependence compared to the other mechanisms. The Larson-Miller parameter exists to help speed up rupture tests, which were quite impractical to conduct over long-time exposures. In order to do so, the tests would be done at higher temperatures while maintaining the same stress, allowing the test a shorter time exposure. The results can then be analyzed by plotting a logarithmic graph such as this one. A way to increase the tolerance of heat-resisting alloys to creep would be to adjust its microstructure. This can be done by reducing the number of grain boundaries, which in turn leads to an increase in grain size. A prime example of this can be taken from the Callister textbook, which describes a polycrystalline turbine blade. A was created through a conventional casting method. High-temperature creep resistance is improved as a result of an oriented columnar grain structure. B was produced by a sophisticated directional solidification technique resulting in columnar grains. However, creep resistance is increased further when single crystal blades C are used. And that concludes today's presentation. I hope you found this presentation useful in better comprehending the creep phenomena, and I thank you very much for your attention.